sklearnmetricspairwisepolynomialkernel. Polynomial kernel. Description. The polynomial kernel is a popular kernel function used in support vector machines (SVMs) and other kernel methods. It computes the similarity between two data points by raising their dot product to a certain power, effectively capturing nonlinear relationships between the data inputs. X a 2D array representing the first set of data points. Each row corresponds to a data point. Y a 2D array representing the second set of data points. Each row corresponds to a data point. If Y is not given, then it is assumed to be the same as X. Outputs. Kernel a 2D array containing the pairwise kernel values between all pairs of data points in X and Y. The shape of the array is len X. Leni. Steps. Calculate the dot product between each pair of data points in X and Y. Raise the dot product to the power specified by the degree parameter. Add a constant term specified by the gamma parameter to the result. Scale the result by the factor specified by the core 0 parameter. Metrics. Accuracy measures the proportion of correctly classified data points. Precision measures the proportion of correctly predicted positive cases out of all positive cases predicted. Recall measures the proportion of correctly predicted positive cases out of all actual positive cases. F1 score harmonic mean of precision and recall. AUC area under the curve, area under the receiver operating characteristic ROC curve, representing the ability to distinguish between positive and negative cases. Visualization plots. Confusion matrix visualizes the performance of the classifier, showing the number of true positives, true negatives, false positives, and false negatives. ROC curve plots the true positive rate against the false positive rate for different classification thresholds, showing the trade-off between sensitivity and specificity. Precision recall curve plots the precision against recall for different classification thresholds, showing the trade-off between precision and recall. Fine-tune parameters. Degree. The degree of the polynomial kernel. Higher degrees can capture more complex nonlinear relationships, but can also lead to overfitting. Gamma. The constant term added to the dot product. It can influence the bias of the kernel. Core 0. The scaling factor applied to the kernel. It can be used to adjust the influence of the constant term. Uncertainty methods. Cross-validation, dividing the data into multiple folds and training the model on different combinations of folds to estimate the model's performance on unseen data. Bootstrapping, resampling the data with replacement to generate multiple datasets and training a model on each dataset to estimate the model's variability. Challenges and fixes. Challenge 1. Overfitting. The polynomial kernel can be prone to overfitting, especially when using high degrees. Sample use case that resulted in challenge 1: training an SVM with a polynomial kernel of degree 10 on a small dataset with many features. Fixes to challenge 1. Reduce the degree of the polynomial kernel. Use regularization techniques, such as L1 or L2 regularization, to penalize complex models. Use cross-validation to select the optimal degree and regularization parameters. Challenge 2. Computational complexity. The polynomial kernel can be computationally expensive, especially when dealing with large datasets or high-dimensional data. Sample use case that resulted in challenge 2: training an SVM with a polynomial kernel on a dataset with millions of data points and thousands of features. Fixes to challenge 2. Use approximate methods, such as Nystrom approximation or random Fourier features, to reduce the computational cost. Use more efficient data structures and algorithms for matrix operations. Consider using other kernel functions that are computationally less expensive, such as the linear kernel or the radial basis function RBF kernel.